Our brain can identify any new sound as it appears in the environment, separate it from other existing sounds, and represent it as a distinct object in our mind. Thus, auditory object analysis requires the fundamental perceptual process of detecting boundaries between auditory objects. However, the dynamics underlying the identification of discontinuities at object boundaries are not well understood. Since sounds may contain multiple components that vary in frequency and time, this process requires a mechanism that monitors the statistics of the time frequency space. So we employed an artificial sound composed of frequency modulated ramps where boundaries were created by changing the underlying spectrotemporal statistics. Subjects were tasked to detect auditory object boundary. Behavior results show robust performance. We collected magnetoencephalographic data from human volunteers. We observed a slow, less than 1 Hz drift in the neuromagnetic signal after the auditory object boundary. This response evoking this drift signal was source localized close to Heschel gyrus bilaterally, which is in agreement with the previous functional magnetic resonance imaging study that found Heschel gyrus to be involved in the detection of similar auditory object boundaries. Time frequency analysis demonstrated suppression in alpha and beta bands that occurred after the drift signal. The induced alpha suppression was source localized to right supramarginal gyrus and right superior frontal gyrus, while beta suppression was source localized to right angular gyrus. So we conclude that new auditory objects in a complex acoustic scene can be signaled by changes in the spectrotemporal coherence. This accumulation of evidence occurs in the primary auditory cortex. Thank you.